All right. Well, I mean, let's get started.
Sure.
I want to keep people waiting. So, welcome everybody to this month's iHack Ottawa meetup. It's brought to you by Red Canary and Yellow Flag Security, our sponsors for the server. Today, we're going to have Dimitri Berioza, Senior Security Researcher at Vectra AI, and he'll be walking us through a challenge for Flare on 7, and the name of the talk is give your brain a break, solving Flare on 7 break challenge. And without further ado, our wonderful guest will take over today's talk. Go
Awesome.
ahead.
Awesome. Thanks a lot, Nadim. Let me share my screen. All right. Okay. Can you guys see my slides? Anyone?
Oh, yes, I
Awesome.
forgot to mention questions and answers channel will be available for everybody to ask questions in real time as well.
Yep.
Or make any comments.
Sure. Yeah, that works. Thanks a lot. And I'll hopefully, fingers crossed, the recording goes well, and I'll be able to post this on YouTube, and I'll just share a link when that happens. And also, as you can see on the slides, the actual slides themselves, they're on GitHub. So if you want to follow them like as a PDF, you're welcome to pull them down and do it that way. It doesn't matter. All right. So we'll be going through Flare on 7 break challenge. Let me. All right. So Dimitri Berioza. I'm on Hackfest Discord usually, and now on iHack as well. If you want to reach me, that's my handle there and my LinkedIn. I do security research at Vectra AI, and we do threat detection in on-prem networks and in the cloud. So if you guys need software like that, check us out. Before that, I worked as a pen tester at IBM Security here in Ottawa. And before that, spent a lot of time actually developing software. Um, I'm primarily interested in reverse engineering and secure software development. I love CDF competitions, and if you participated in CDF competitions in Ottawa, for example, we may have seen each other. And I'm currently in Ottawa, but originally I'm from Russia. So what we're gonna talk about. So first I'll touch on what Flare on actually is. Not everybody knows that. I'll do the overview of this challenge and describe different protection mechanisms that they use to make reversing tougher. And then I'll go 3 different solving stages, that are inside. And then we'll wrap up. So what is Flare on? If you're into reverse engineering, you may have heard about this competition. It's annual reverse engineering competition that's organized by FireEye, the famous cybersecurity company. It's in its 7th year, though this year will be 8th year. Usually occurs August-October timeframe. Every year it's on a different date, so it's hard to say. You have to watch their Twitter and their website to see when it actually starts. And usually they have between 10 and 12 challenges of increasing difficulty. They start with really simple stuff and end with kind of nightmarish kind of challenges. You get 40 days to complete all 12 challenges. It may seem like a lot, but it actually isn't. And once you try it, you realize why that is so. Things get really, really tough at the end. So I made this statement several times in the past, and no one has challenged me on it. This is the toughest RE competition I've seen so far. If you know something that's very interesting and tough in reverse engineering, Please let me know. I would really like to know. But for now, I'll keep claiming that this is the toughest one. And what's really interesting and unusual for online competitions, if you actually finish it in time, you get a prize. And every time they get a different prize created and sent out to people. So last year, apparently, it was a key. It's interesting if you've done CTFs online before. It differs from them in several ways. So first of all, you can only solve challenges in order. So if you get stuck on challenge number 1, you cannot proceed until you actually finish it, and then challenge number 2 opens up. So it's not like you can try number 5 and then switch to 11 and kind of keep switching back and forth. You have to really solve them in order. Flags are in kind of a weird format. They all look like email addresses. I don't know why that is. That's their choice, I guess. It helps to know that there's certain constant part at the end. For some challenges, it actually helps you to solve them. Just I thought kind of an interesting choice for a flag format. And because this is a cybersecurity company, they deal with real malware a lot. Many of these challenges are actually based on real malware samples and malware techniques. So it's not only kind of an intellectual exercise. It has real-world use. You can learn a lot of techniques that you can actually use later on in your day job if you work in cybersecurity. Another interesting thing is that everything there is solvable with free or open source software. You don't need to buy any kind of license to be able to solve these challenges. You don't need IDA license, for example. So the free tools that are out there will be enough. And they actually provide you with something called Flare VM. It's a virtual machine based on Windows that's just filled with all kinds of software that helps you do reverse engineering. So it's like a Kali VM, but geared towards reverse engineering. So that's kind of interesting, I guess. So what kind of challenges are there? And the answer is any kind. Literally, like I did this competition several times. They have everything under the sun. So first of all, any platform you can think of, any mobile platform you can think of, different P-code challenges, the ones that get compiled into this kind of bytecode intermediate representation, like Java and .NET. Different scripting challenges. I've seen obfuscated VBA, PowerShell, and others. Web-based challenges, where, let's say, JavaScript is obfuscated, or when you need to reverse WebAssembly. A lot of third-party tools that get compiled into executable-like format, where there's some kind of bytecode that gets executed by a tool. Kernel drivers, shellcode, embedded applications. Some esoteric challenges where the language they're using is really, really unusual, like sublect, for example, if you're familiar with that concept. Also custom VMs, where a program gets compiled into an intermediate representation that's executed by like this mini virtual machine that is able to interpret custom-made bytecode. So it's essentially an instruction set that's just made up, and there's a sizable program written in that instruction set, and you still have to go and reverse that. And on top of that, they have obfuscation, encryption, all kinds of anti-debug, anti-analysis techniques, just anything imaginable. So it's really, really fun if you're into that sort of stuff. So last year, it was Flare 7. They had 11 challenges, and you can see the number of players per challenge solved. So actually over 5,000 players started the competition, and only 3,500 solved the first challenge. And the first challenge is usually really, really simple. It's sort of like if you've done CTFs before, the fairly simple level 1 reverse engineering challenge where flag is really easy to find. That's the type That's usually challenge number one in this competition. I guess they're doing it so that people don't get discouraged and start easy. But then things really escalate really quickly. So last year, only 260 people actually finished the competition. So they were able to do all of the challenges in those 40 days that were allotted. And if you're curious what challenges were there in the competition, they actually posted both the challenges and the write-ups from the challenge authors on their website. So you can go and play with them and check them out. So actually, let's jump right into challenge break. It was number 10, so it was more on the complex side of things. So as I started looking at it, it looked fairly simple on the surface. So it's a 32-bit Linux executable. It's not too big, just over a megabyte, and had a very, very simple command line interface. A couple of messages are printed out. Enter the password. You enter the password, and it tells you whether password was correct or not. So good enough so far. However, immediately, if you're paying attention, there was a part that was immediately concerning because it didn't output what I entered. It printed out something else. And later, my kind of worst fears were confirmed that there's much more going on under the surface. So in this presentation, I decided not to do the live disassembly debugging session. I decided to go with slides because the challenge is tough enough that it's very easy to get lost in the details, and you guys just won't enjoy the presentation. So I'll just display selected disassembled pieces and cleaned up decompiled code and sometimes pseudocode so that things are easier to understand. So if we do decompile in something like Hydra, for example, the code couldn't look simpler. A couple of print statements, you read the password from command line, it checks the password and says yes or no. The password is correct and not correct. And the decompiled check password routine also brain dead. Just a string compare to a constant value. Looks, yes or no. Is it correct? Does it match? Doesn't it match? So immediately, like if you think back to the previous slide, this message at the bottom where it says printf sorry, but this is not correct. You may remember that it printed sorry, but I stole your input is not correct. But you can clearly see from the code that it outputs the buffer contents, and the buffer is what the password was read into. So that's a bit of a mystery that will unravel later. So when we actually go and take this hard-coded password that's in the source and enter it, it doesn't accept it. So why? That's that's the mystery. So it turns out that there's much more under the hood. First of all, if you look at the very start, even before libc start main is called, there's actually an initialization procedure, or actually set of procedures are set up. And as I went and reversed those, there actually was a lot of code in those initialization procedures. So first of all, the first big one was actually forking the process. And those of you who are not familiar with fork on Linux, it basically takes your running application and spawns another copy of it, and execution continues in that second copy of the application in the child from that point. So it's like your process is split into two parts, and depending on what result, depending on which way, which process it is, the result of the fork function will either, I think, return null if it's the main program, and not null, it will return the ID of the child process. I think that's the way it works. So forking actually creates the second copy of the process, and then there is a huge function that's processed after that, and I'll go into more details a little later. And as I keep kind of unraveling that code, so the child application that gets started, that huge execution loop, it does all kinds of processing, dispatches and receives messages, and there's just a lot going on. You can see from the diagram that there's quite a bunch of logic in there. But that's not all. At some point, and yet another process gets spawned using fork again. So now you have 3 processes running for this challenge that looked fairly simple on the process, on the surface. And in that challenge, another big control block is started. So there's another big set of functionality, big execution loop, also processes and receives and dispatches messages. So these 2 blocks are actually the meat of the challenge. That's what we actually need to analyze and figure out what's going on. So in those blocks, there are actually several very interesting mechanisms. The first of all, for its execution, this challenge uses ptrace. And those of you who are familiar with Linux, ptrace is the mechanism that Linux uses for debugging. So all your debuggers and trace tools are actually based on this mechanism. So that right away that makes debugging impossible, because ptrace is actually used for challenge execution for its logic. So that's the mechanism they use to complicate things for you as a reverser. It uses signals, but uses them for actual communication. It sends parameters with signals, which was kind of an interesting way of doing kind of code flow control. And also it uses system calls, but in such a way that a system call that usually means one thing, it actually in another process, it's caught and reinterpreted as completely different thing. And I'll show you how it all fits together later. So all of this is not good, because it makes debugging pretty much impossible. You have 3 processes that they're using all these mechanisms to communicate with each other, and there's just no easy way of setting up a debugger without doing all kinds of, I guess, development and putting some kind of control scaffolding in place to kind of manage all of that complexity. So this is how processes fit together. So when you run it, you actually see these are 3 processes. There's a parent, there's a child, and a grandchild. And so when the parent forks the child and the child forks the grandchild, the ptrace is actually used to control execution of the ancestor. So grandchild ptraces or debugs the child, and the child debugs the parent. So that was kind of upsetting, to say the least. And parent communicates with the child, and child communicates with the grandchild using signals and syscalls. That was a very unusual way of doing it. That was the first time I was seeing this. So how does ptrace actually work there? So there are several types of standard ptrace operations that are used in the challenge. There's setregs. So when you're debugging a process, so in this case, child debugs the parent. You can when the process you're debugging is suspended, you can change values in its registers. So setregs and getregs manipulates the registers. You can use peek data, and poke data to modify memory blocks. You can set a word at a certain address in the process that you're debugging. And there are also attach, continue, and deny attach, and those are just for flow control. So you can, for example, you attach to a process you're debugging, and let's say when you're done modifying its registers, you continue that process to let it keep running. So that's basically what I just said. You use continue, attach and continue to control the execution flow, and when the process you're debugging is interrupted, you use these other methods to modify registers and memory locations. So signals are also used in a very interesting way. Children here use no, sorry. So I guess the parents uh, uh, use signals to convey information to the children and trigger special functionality that gets executed there. So the first signal it actually fired when an illegal instruction is being executed. And what they did here, they placed an intentional illegal instruction that's not valid in Intel processor to trigger this signal to transfer control to another process. They used segmentation faults to trigger memory violations by just calling a null pointer to also trigger certain types of functionality and to transfer control from the parent process to the child that way. And remember, the child debugs the parent. They used an alarm for another set of functionality. I think it was for creation of a grandchild process. And seek trap can be used for catching all kinds of exceptions. And in this case, they set it up so that it would catch execution of system calls. And I'll on the next slide I'll explain how that works. So basically, every time in one process a system call is made, it gets trapped in the process that debugs it, and completely different functionality gets executed there. And there are also other signals they catch and process, but that's mostly for preventing against premature shutdown. So system calls. System calls are just regular, functionality in the kernel that user applications can call. And as I said, the processes are using these to execute something completely different, and it's caught by another process to actually make that happen, and that's done using seek trap. So here are some examples of the overridden functions. So the first one was execve, and again, those who know familiar with Linux, this is for executing an OS command, and the purpose for which it was used in this case was very benign. It was just removing a new line from the end of the flag that user entered. However, it was called with these parameters that it was horrifying, because those who understand it means that if it were to be executed without any catching of the signal and processing, it would just obliterate the file system. And I actually read on Twitter that one of the guys that tried to solve it accidentally did kill his file system because he was debugging it and actually let that call execute as is. So needless to say, that was one of the things I patched immediately, because that was just too dangerous to keep executing. But in this functionality, those parameters are just ignored altogether. So it doesn't have that effect that it seems to have on the surface. So some other system calls were like set priority, for example. It actually decrypts a string that you give it. mlock all counts the number of 1 bits in the parameter. Read is overridden to read the user flag and also replace it with another string that says, sorry, I stole your input. So that actually explains what we saw at the very beginning. That's how they take this input from the user and override it with something completely different. And there were others. There were about I think 12 system calls that were overridden. But that's not all. They use encryption all over the place, multiple encryption algorithms, from simple XORs, so I think there were several varieties of those, to custom encryption. So that was fun to deal with. And they encrypt both code and data. There were lots of decoys to kind of distract and infuriate you. So there were a lot of false flags, of course. There was shell code that was unused, was just thrown in there just in case. And taunts. There were taunts all over the place. There were, you're wasting your time, blah, blah, blah. It was just, when you're stressed and you're trying to solve it, it really doesn't help. So how do we even approach something like this? Because debugging is out. What can we do? So there are actually several things that we could do, and there's several techniques, and I use them all pretty much. So first of all, static analysis. I would say in most reverse engineering challenges, even the ones that you can debug, I think you need to do some static analysis, at least to understand what's going on, at least in broad strokes. Because debugging was restricted, it made static analysis that much harder. But it had to be done. There was no easy way around it, so I spent a lot of time just going through the code and decompiling and just trying to piece together different parts of it to see how the execution flow actually works. Selective patching works because as I tried to execute certain pieces of the code, I needed to disable parts of it, at least the parts that actually start debugging. And some parts that get signals initiated. So that was helpful. Also, even though you cannot debug the challenge as is, you can do some selective debugging. So the trick that I used, for example, was I would set a breakpoint before the fork and before any ptrace calls were initiated, and then I would jump to a piece of code where I know there was, let's say, an encryption algorithm that I wanted to execute, and I would manually set the registers to have just the right values, and then step the encryption algorithm. So that helped a little bit. I didn't have to rewrite everything from scratch just to do decryption. But you have to be careful. You have to do breakpoints a lot. You have to patch parts of the code, so it's not pretty. And unfortunately, I had to re-implement some of the code. I'll show you later how I did that. Python was a big help here. And finally, to truly understand what's going on, I had to build sort of a kind of a monitoring scaffolding around this challenge. So even though this thing is being debugged and it's impossible to use things like strace, for example, you could still use this trick to track the calls that are being made and function and the system calls that are being made, and also what kind of ptrace functionality is being executed. So I wrote a little C shared library that would re-implement a bunch of system calls that are used in this challenge, and basically it would add a printf statement to output parameters that are passed to each system call, and then call the original function, and then after that output the result, the result of the call, so that as the challenge gets executed, you get a big log of different calls that are made, in what sequence they're made, what are parameters that are passed, and that helped a lot with kind of understanding the execution flow and seeing what data gets passed there. And this is how it's loaded. You basically just compile it as a shared library. You'll use LD preload to load it before the challenge, and the challenge, when it does a call to truncate, for example, it first goes to the shared library, data is logged, and then the call gets actually dispatched further on and processed the regular way. So that helped a lot. The logs get pretty big though, so it took a while to analyze them. So how I actually proceeded, like once I understood all these pieces, I could actually proceed with kind of understanding what the different stages are in analyzing different parts of the flag, because that's how it actually works. There are three stages, and each stage is processing or verifying a different part of the flag. So the first stage is triggered by that illegal instruction that I mentioned to you. So that there is a sig-ill signal gets thrown, and the first section of the flag gets checked. And I'm specifying addresses in here. They won't mean anything to you, but if later on you decide to take a look at the challenge, maybe they'll help you analyze what's going on. So what the code does, and I'll show the decompiled version a little later. So that the code in the first stage takes an encryption key that is itself encrypted. It's stored, so encryption key is encrypted and stored in the code of the challenge. But there is this nice function that's usually used to change the process priority on Linux, but here it's overridden to decrypt internally stored static strings and pieces of data. So this function, as part of execution, actually decrypts that encryption key, so it's now in the clear. And then that key is used to decrypt hard-coded ciphertext that corresponds to the first 16 bytes of the flag. And then the plain text, the first 16 bytes of the flag that you entered, is actually compared to that. So if you're paying attention, actually, this is really helpful, because it doesn't mean what you enter. If you can debug up to that point, up to that if statement, you can get the first part of the flag in the clear, even if you don't know the flag, or it doesn't matter, because at the point where the comparison is made, that hard-coded encrypted part of the flag is already decrypted and is ready to be compared with what you entered when you interacted with the challenge. So that was kind of a big help there. So there's a decrypt function here that gets called 4 times for 4 different bytes in this 16-byte chunk, and the flag, that first portion of the flag is revealed. So so I actually did that trick where I did selective debugging before any kind of forking or p-tracing is done, by just changing the program pointer and manually adjusting the registers to be just the right values. And that's the first part of the flag that gets revealed. So it's welcome to the, and then letter L, or number 1. It's hard to say what it is. All right, so far so good. So then comes the more complex stage that was much more labor intensive to analyze. So here they actually make a lot of use of the fact that there are these 3 processes, and in executing the logic in the second stage, they actually jump between these processes a lot. So I had to kind of manually analyze the logic and re-implement it in Python. And that's what also made it necessary, was that for the second stage, they actually made it, they didn't make it as easy as for stage 1. They actually took the second portion from the flag that user enters, they encrypted it, and then they compared it to encrypted representation that was stored in the body of the challenge. So I had to kind of not only re-implement the algorithm, but I also had to kind of build the inverse logic, because they only had the decryption code. Sorry, no, they also only had the encryption portion of the algorithm available in the challenge. I had to build the decryption portion, and that meant reversing logic in part of it. So interestingly, the decryption key for decrypting this second stage was actually a checksum of string. This string has no purpose and is merely here to waste your time, which was hilarious. Apparently not everything that looks like a decoy is actually a decoy. So that was a lesson learned for me. And so they use this checksum function that is probably like CRC of some kind, like CRC32 or something. So I wrote this decryption script, and I basically just had to piece it together by analyzing what's in the challenge and kind of carefully experimenting and inversing some of the logic to make sure it all works. So the part at the top, this big byte array, is the encrypted representation that actually stored in the body of the challenge. And then the setup function is something called key scheduling routine, and it's invoked for every round of decryption. That's very common in encryption algorithms. So that's the first part of the script. And the second part of the script is the actual decryption algorithm. The key in here is that decryption key that I talked about, the one that's the checksum of the big string. So I just hard-coded it in. And as you can see, it operates on 32 bytes of the flag that user entered. And it works in 8-byte chunks. So it goes and runs this loop 4 times and decrypts this data in 8-byte chunks. And when it actually prints it, we actually see the second part of the flag revealed. So now it becomes "Welcome to the land of death and destruction." End. That's interesting. But that's stage number 2. There's a third stage also, which is was very interesting in its own right. So if you think back to the previous slide, I only decrypt 32 bytes of the flag. But in the real code, it actually decrypts much more than that. There's a big chunk of data encrypted inside the challenge, and it's 40 kilobytes in size. So what could it be? It was just kind of mysterious, and it actually goes and decrypts it all. So when I thought at first I thought it was some kind of like an image or something, but you'd probably never guess what they put in there. That was I don't know where what they were thinking, where they were designing this challenge, but the guy that did it has really an interesting mind, I think. So the data in that block was a full script for the B movie, and I don't know what made him put that in there, but that's what it was. It was just a full text with all the roles split up, and you could do a full readout of the B movie by just going through that script. It's just, I don't know, it looked like another decoy that he was just messing with us. No, of course, it's turned out to be something deeper than that. It's the text of the script, but there's something interesting going on inside. So this script is being processed by a truncate function, and Linux is just a system call that I think truncates the file to a certain size. But of course, since they're overriding system calls, they gave it completely different functionality with a completely different meaning. So that function looped over the data, and the logic in their implementation of that function, it's set up in such a way that it will actually trigger a buffer overflow when you pass the 16,000 byte mark. But that only happens if there is a 0 byte beyond that. And if we look closely inside that that film script, at position 16,168, there is actually a 0 byte in there. And what's more, the buffer overflow is set up in such a way that it actually jumps to an address that's embedded in there right before the 0 byte. So there is an address 805.3b70, and that's where the control is transferred if this buffer overflow occurs. If you do some math here, so we have this address, that's the first number, and the second number is where in memory during execution time this encrypted script is located. So if you subtract one from the other, you get address 7530. So essentially, it will transfer to that address, to that offset, within this big chunk of text. And when we look there, there's actually binary code in there at that position, which is a piece of shell code for decoding the third part of the flag. That was just mind-blowing. So once I traced all that, I could actually analyze the third stage of this challenge. So the shellcode is pretty big, like 5 kilobytes. I think it's not very common, and there's a lot of functionality in there. I spent a long time analyzing it. At the end of it, you see a few hexadecimal numbers. They're very long, and they're stored as plain text strings. And inside the code, they're actually transferred to real large numbers. And as I went through functionality inside the shellcode, it was a little confusing at first, but with more analysis, I realized that it's a big library for working with large numbers. So it can take this large hexadecimal number, convert it to a number internally, and it can compare two large numbers, it can copy numbers, it can divide with remainder, it can multiply two numbers. So it does primitive operations, but on really huge numbers. And if you think about it, like how would you approach, for example, adding two large numbers? They're too big to fit in the registers. So the simplest way of doing it is just doing loops over chunks of these numbers. So let's say you take the lower, I don't know, 4 bytes, for example, of this number, you add them together, you take a carry, and then you add the next two chunks, and then keep carrying numbers, and little by little, by doing kind of this loop, you can actually implement the add operation for two large numbers. And that's exactly what this library is doing. So once that became clear, I could actually kind of take the bird's eye view of the functionality and understand what it's doing with those numbers. There's actually a main function in there. Well, main, quote unquote, it's not like main in the C sense. It's the function where the functionality actually starts working. And it's at that address, DBE. And after you kind of analyze and ignore the parts that are irrelevant, and it took a while to analyze, what remains is actually fairly simple logic. Load 3 big numbers. It loads more than that, but others can be ignored. They're not important for this calculation. So let's call those numbers A, B, and C. And then take 24 bytes of the flag at position 48. So that's the last chunk of that long flag. And let's call this number X. And what it does is it tries to solve that equation, basically. So X times A modulo C should equal B. So essentially, if we solve this for X, we'll find our last chunk of the flag. So how do we do this? I've seen problems like this in CTFs before, and my kind of go-to solution is Z3 Solver. It's a tool built, I think, by Microsoft, and basically solves equations like this. So you can import the library, you can specify your variables that you want to solve for, and then you just call the solve function, and if you kind of do everything correctly and your expression is just right, then it will come up with a solution. Unfortunately, for this library, it choked on numbers as big as this. I think it just has some limitations. It can solve expressions with smaller numbers, but just not as big as these. And I actually tried this exact expression with small numbers and solved it instantly. So it's not I guess it's not a problem of how the expression is formulated. It's the size. I ran it overnight and still couldn't come up with an answer. And I was stumped for a while, but this is where kind of good, careful recon comes into play. It's important to understand the challenge you're trying to solve fully. So as I was decrypting different hard-coded strings in there, there was one that kind of caught my eye, and was I hear Wolfram Alpha is good at doing things with big numbers, and that was the light bulb moment. So I actually went and used Wolfram Alpha to solve that equation. So it's not the easiest thing to use for large numbers. Also, like I guess they're not expecting people to, to post numbers that are as big as that, and it chokes. It basically the expression that I showed in the previous slide. It's so long that it actually, when you post it in the web form, it cuts off a portion of it and just says, I don't know what you're trying to do. So I had to kind of get creative. I first did a really simple equation that, as you can see, it's equivalent to what I'm trying to solve. It just works with really small numbers. And once it solves that, there's actually a button that appears in there that says continue in computable notebook, and that's what saved me. So once I went into the notebook, you get an interface where you actually build a sizable expression in there. So I just replaced these constant numbers with my numbers, and instantly it gave me an answer. So it actually gave me a really long number. That's the answer for X. And once I took that and I converted it to hex, and then just did some manipulations to convert hex to back to binary, and I had to also reverse the order because this is a little endian architecture. That revealed the last portion of the flag, which is the full flag now is welcome to the land of death and destruction and no puppies at flareon.com, which is hilarious. And then, so now this is our flag, and once you plug it into the challenge, it takes a while to actually compute, because I think the way they implemented the decryption algorithm for that huge chunk, it actually takes a while for it to work. So you have to wait for about 30 seconds before it actually comes back, but it does come back and gives you an answer. Yay. All right, so to wrap up, so this was kind of, I guess, the worst case combination of various reverse engineering avoidance techniques that I've seen so far. So I've never seen ptrace and signals used for execution before. That was just amazing. Like I imagined it before, like that they could do it, but I didn't. I've never seen it used to this degree, like where everything is pretty much based on that. Function overrides were really frustrating because you look at the code, you see that it's one function, and mentally you have to kind of switch and realize that the function that says nice is actually a decryption function. That was kind of frustrating trying to understand that. A lot of decoys that you have to ignore, custom encryption, complex calculations. So it was really a big job, really frustrating to deal with. But once you get through it, it's really satisfying, and you look back and you just marvel at how much you learned as a result, and that's what this is all about for me, really. So if you're interested in reverse engineering and you haven't tried Flareon before, I highly recommend it. I think it's a great competition to try, and you will learn a lot of techniques that maybe you've never would have worked with before. And there's a great variety there. These challenges are built by really smart people, you could tell, and they are also have real-world application, because some of this code is actually stolen from real malware that they analyze, and when you download these challenges, my antivirus, for example, it just goes crazy. It goes nuts because it notices these malicious patterns that were neutered for the purposes of this challenge, but they actually come from real malware samples out there. And that's it. If if there are any questions, guys, I'll be happy to answer them. And otherwise, thanks a lot for listening.
Thank you very much, Dimitri. So this is a pretty complex problem to solve, just based on what you described. What do you suggest? You know, if what's like, what kind of workflow do you use when you're tracking all of these different elements? How do you organize basically, your thought process, your problem solving?
Yeah. It's every time it's a learning experience because they throw something new at you and you have to kind of regroup and learn on the on the fly. So I have as I mentioned, I did a fair bit of software development, so I have a certain mental picture. I think of when I see a challenge like this, I try to imagine how it was developed. That kind of coming from software engineering background helps. Staying organized helps. As I go, let's say in IDA, for example, or Ghidra, it really helps to kind of be really methodical. To, as you, let's say, you understand what a certain function means, you immediately rename it to give it a name that makes you understand what it does. You add comments all over the place. You when there's, let's say, some kind of magic number is used somewhere, you immediately change it to make it an enumeration, and give it symbolic name that you understand. Yeah, so comments, meaningful names for functions and numbers and variables. That really helps. And it also helps that you can kind of it's not the regular CTF where you have, let's say, 2 days and you're done and you're really stressed and you have to rush and you don't have time to think. The fact that they give you 40 days, you can go and sleep on it and then come back the next day refreshed and attack it again. And so that also helps a lot. You can step away, and your brain, like when I find that when I'm trying to solve something, the fact that I stepped away from computer doesn't mean that my brain stopped thinking about it. It actually keeps, I think it keeps churning, and you may, maybe in the shower, and then, bam, the solution comes to you. So taking breaks is also a big help.
And how long did this take to solve?
This particular one took me about 2 weeks. I spent just a few hours every night.
Well, just a reminder to everyone: if you have a question, post it in the question and answers. I think we have something in there. I don't know. Takeaway for this was: don't forget to take showers.
Yes. Yeah, great tip. Yeah, thanks.
Any other questions from the crowd? In terms of software that you've used, you mentioned Ghidra.
Yeah,
You find that there's any other kind of, and Python, any other kind of tool
yeah.
sets that you've used in the past that help in these kinds of challenges?
Yeah, I like IDA a lot. I think it's very mature, and there's a free version that you can download for Windows, for Mac, and for Linux. It's limited. If you can get a license from your employer, uh, it would be a great help because you can do things like remote debugging, and you get a lot of additional features. And also, IDA has decompiler, so if you can get that, excuse me, that would be a great help. But Ghidra has a decent decompiler, so I find that kind of alternating between IDA for debugging and analyzing the binary code and jumping into Ghidra to decompile pieces of code helps. Can give you that bird's eye view of things. Yeah, but other than that, there are lots of other tools. Like it really depends on the challenge because sometimes they would throw a VBA, the Visual Basic for Applications thing at you, and that you will need to open it carefully. And there are certain tools, for example, in Python for analyzing and dumping embedded scripts out of Word documents, or they'll give you a .NET executable, and I think ddot is the tool to work with that. There are Java decompilers that you can use for Java challenges. So there is this whole menu of things that's available depending on what you're reversing. And that VM that I mentioned, Flare VM, is really useful for that because they dump like a lot of tools in that VM.
Awesome. And for people starting up in, reverse engineering, what would you recommend? How should they start their journey?
I actually did a talk at Hackfest exactly on that topic, but I think the recording is not posted yet. So I addressed it there at length, kind of my suggestions on that. I would say, first of all, I think you need some kind of experience with developing software, even the simple stuff, because if you are not familiar with a programming language, let's say like C, it's really hard for you to take a compiled executable and have a mental model of what it does. So some limited experience developing programs, even really simple ones, I think it's kind of prerequisite for that. But then what you could do is write a very simple program like Hello World, compile it, and then try to reverse it. And what helps here is that there's no guesswork. You know exactly what's supposed to be in that executable, and you can actually go and look at the code and confirm your expectations. And once you've mastered that, what you've tried doing these really simple challenges that you've done yourself, then you can graduate to the next level. You can start doing simple crack me challenges, which are there is like a multitude of them on the web. There are all kinds of challenge sites, like Ring Zero, for example, is the one I think some guys in Quebec are maintaining. Has a lot of challenges on it, including reverse engineering that you can start with little by little. Playing in CTFs helps because there you're actually under the gun to learn something quickly, so that kind of gives you a kick in the butt, so to speak, to jumpstart your learning. So learning little by little, experimenting, I think is the way to go.
Awesome. And are you playing for any CTF teams for NorthSec?
Yes, yeah. We have our own old IBM team. It's called Ministry of Penetration. So yeah.
I think we played against you
Yes.
in Hackfest, right?
Yes,
the
that's
Ministry
right.
of Penetration.
That's right. Yeah.
Yeah, we came in second to the Gliderius Tigers, I believe the name of the team was. And Alex is on that team. He's also on the stream. All right. I see some people typing. Okay, nice walkthrough. Thank you. Great presentation. I don't have any more questions, but this Discord server is here for everybody to hop onto and ask questions and interact. We're trying to get this community kick-started. I'm just going to share my screen right now just to let you guys know what's up. In terms of, next month, I believe that, I don't know if everybody can still see the slides right now, if I can get an okay.
Let's
but
see. Yes, I can.
All right, awesome. So for next month, Gustavo says that he's going to do presentation. I'm still waiting on the abstract, my friend. I'm going to let you defend yourself live. So you can talk, Gustavo, if you want to. But next month we are looking for a speaker. If it's Gustavo, he's got some ideas. We're more than happy to have you, Gustavo. He's from Brazil. And as I said in the last meetup, we are always looking for people to volunteer and help us grow this community. We're starting this. It's a fresh community. It started small. but we want to make it big, and we want to, we want to make Canada a cybersecurity hub for just like DEF CON in the world. So, big ambitions. We're going to get there piece by piece, and we're looking for guys that are community leaders, that can organize events, guys and gals, I should say. And yeah, you can reach us in any one of those methods, and also on this Discord server. Finally, thank you for attending. It's always worth it to be able to come together and share our knowledge. And we look forward to doing that on a continuing basis, throughout until the Earth, I guess, disappears due to global warming or whatever. But we are here. We want to stay strong, and we really appreciate you guys coming out and sharing your knowledge. So thank you very much for attending. And I'm just going to make sure there's no more questions there. All right. Gustavo says he's going to do it. So waiting for you, Gustavo, to share the abstract and let us know what you're going to be talking about. So we'll see you. So we've set the cadence for the last Tuesday of every month. We'll see you guys on the last Tuesday of next month, and we'll have the details up on our Discord. Cheers, guys, and thank you for coming out.
Awesome. Thanks, guys.
Thank you, Dimitri. Thank you for presenting as well.